How do decoding algorithms correct quantum errors? Imagine trying to fix a puzzle with missing or misplaced pieces without knowing exactly where they belong. That's similar to what decoding algorithms do in quantum computing. They help correct errors that happen during quantum calculations, keeping the information safe. Quantum computers use tiny particles called qubits to process data. But these qubits are very sensitive and can easily be disturbed by noise or faulty operations. To protect the data, scientists use quantum error correction codes. These codes hide the original information across many physical qubits, creating a kind of backup system. During a quantum process, the system performs special measurements called syndrome measurements. These measurements don't look directly at the data but check the relationships between qubits. The results of these measurements form a pattern called a syndrome, which hints at where errors might have occurred. Once the syndrome is obtained, it is sent to a classical computer. Here is where decoding algorithms come into play. The decoder analyzes the syndrome data and tries to figure out the most likely errors that caused it. It compares the pattern to many possible error scenarios stored in its memory. The goal is to find the best match that explains the syndrome. After identifying the errors, the decoder sends instructions back to the quantum processor. These instructions tell the system which corrections to apply to the qubits. By doing so, the errors are reversed, and the quantum information is restored to its original state. Speed and accuracy are both vital for decoding algorithms. If they are too slow, errors can pile up faster than they are corrected. If they are inaccurate, they might miss errors or introduce new mistakes. To improve performance, modern decoders often use advanced techniques like machine learning. Neural networks can learn from real hardware data to recognize complex error patterns more effectively than traditional methods. In real-world experiments, such as on Google's Sycamore quantum processor, advanced decoders have been tested with surface codes. These decoders adapt to the actual noise in the hardware, even when the exact error model is unknown. This flexibility is essential because noise in quantum systems can be unpredictable and complex. Today, researchers and companies are creating tools that allow real-time decoding and correction. These tools combine quantum and classical computing, working together to keep errors in check during long calculations. This progress is bringing us closer to practical quantum computers that can run complex algorithms without being derailed by errors. In essence, decoding algorithms interpret syndrome data, identify the most probable errors, and instruct the quantum system to fix them. This process repeats constantly during quantum computations, making the system more reliable. As hardware improves and decoding techniques get better, the dream of fault-tolerant quantum computing becomes more achievable. Understanding how decoding works helps us see how quantum computers will someday solve problems beyond what traditional computers can handle.